Hey, welcome to the last section in this chapter. We are going to talk today about a couple of different things. One of them is really just reversing the process that we did in the previous section. In the previous section, we were differentiating inverse trig functions. So today, we're going to see what happens when you anti-differentiate something and get an inverse trig function as a result. So obviously very, very related to what we were doing, and we'll talk about that in a little bit in more detail. We're also going to be looking at a couple other sort of obscure integration techniques that are nonetheless worth talking about because they come up in pretty much any college calc class you ever see. So let's start with the reversing last section's process. So in the last section, we talked about how if you wanted to differentiate arcsine of something, you could just do the derivative of the something over 1 minus the something squared in a radical. We talked about how to get derivative of arctangent, and we talked about how to get derivative of arcsecant, or inverse secant. It turns out if you integrate both sides of this equation, you get a whole new equation that is pertinent to what we're going to be doing today. So if I integrate the left side of this equation, which is itself a derivative, if I integrate the derivative, I get just the regular old function by itself. If I integrate this, I get arcsine u. And if I integrate this right-hand side, I get the same thing except inside an integral. Now I am going to call the u prime, I'm going to call that du, because in an integral we use differentials, not derivatives, but they're quite related. Same thing here. If I integrate the left side, I'll just get arctan u. And if I integrate the right side, I'll get the same fraction inside an integral. Again, my u prime is a du. Same thing here. If I integrate the left side, I get just plain old arcsecant. And if I integrate the right side, I get the same thing, but in an integral. So this section is all based off of these integration patterns. We're going to get integrals where we have this kind of pattern to it, and we got to just sort of recognize, oh, that's that arcsine function, or oh, this thing is an arctangent function. Or remember, if it were this with a negative in it, we could then call this the cofunction over here. This would be arc cosine instead of arcsine. So let's put this all together on our notes sheet. The integral of du over this pattern, now they have this even a little more specific. They don't just have a 1 here the way we did in the previous section. They actually have any constant you want squared. So in all the problems we looked at before, a was 1, and then a squared would still be 1. But what you're getting here then is an arcsine pattern. The quantity, though, isn't just u, it's going to be u over a. And that allows for this constant to be something other than just 1, plus some constant of integration. This pattern would result in an arctan pattern. But again, there's an a here, which allows for some constant other than just 1. And what you would get is 1 over a times arctangent of the quantity u over a plus some constant of integration. Ooh, that's better. Finally, if you have a pattern like this, you're going to end up with an arcsecant result. Again, this a here allows us to put 1 over a out front. The quantity of the arcsecant is going to be absolute value of u over a, and then we'll have a plus c tacked on. Now look, I don't expect you to memorize these. However, what I will typically do on tests and quizzes is I will just give you this printed on the test, and I will expect you from there to be able to figure out what the derivative of arc sine is, what the derivative of arc tan is, and what the derivative of arc secant is. Because you can read this thing backwards. The derivative of arc secant something is going to be the derivative of the something over something times square root that thing squared minus 1, basically. So you have to know how to read these patterns backwards. That's what I expect out of you. And I expect you to know that if this is arc cosine, that there will simply be a negative in front of the derivative. Same with arc cotangent would have a negative with the derivative. Now, knowing these three integral patterns doesn't mean that every single problem we see in this section is going to necessarily involve an arc trig result. So it gets mixed together a little bit, just like life. It's not always one tool for every situation. In fact, we see in this first example here, there are two terms in the numerator. None of these three patterns have two terms in the numerator. But knowing what we already know about math and algebra, since there's two terms in the numerator and essentially one term glued together with a square root in the bottom, we can write this as two separate integrals. One of these integrals is going to fit the arc trig patterns that we see above. The other one we can integrate with stuff that we already knew. If you can't use power rule, u sub is always a good path of least resistance to try first. If I were to do u sub with this integral, I would probably let it equal the denominator. And then du would just be negative 2x dx. The denominator we could write as u to the negative half. And then by putting du in there, we're knocking out the x and the dx. We just have this stupid little negative 2 that isn't supposed to be there. But we can take care of that. It's a constant. We can balance that with a negative 1/2 out front. Now if we're going to integrate this thing, now we're looking more at, let's see, there's a square root and a constant here. Now we're looking more at like arc sine. There's a square root of 25 minus x squared. What if we let u equal x, which in regular u sub, you wouldn't do that. If you were doing u sub and you're letting u equal x, you're just exchanging one variable name for another, and you're really not making any progress. But here, it's more complicated than that. There's constants involved as well. So we can let u equal x, du would result in dx, and then we have this constant here, a squared is 25, which means that a is just plain old 5. So if we rewrite the first integral, now we're back in just plain old u sub mode. What we have is a negative 1/2 out front to kill off this negative 2. The denominator we can take care of by saying u to the negative 1/2 power. And then when we put our du in here, since the negative 2 is no longer an issue, we're killing off the x and the dx that was written in the original problem. Here we're going to go into arc trig mode. This 1 dx can be replaced with simply du. This is 1 dx. Underneath we have a square root. Inside the square root we have something squared, so we have 5 squared minus x squared is u squared. So this 5 is our a. So we are meeting this pattern directly. So now both of these integrals are things we can handle. Using power rule, we're going to go up a power, so that's u to the positive 1/2. If I call that over 1/2, it's the same as saying times 2. This is going to be arc sine of u over a, which would be x over 5 plus a constant. And to tidy it up, this half and this 2 multiply together to give you just 1. U to the half is really 25 minus x squared to the half. Or instead of half power, I'm going to call it square root. And the rest of this just plays out. And you get your answer. Another example on the back. All right, so on this next example, I would try, I'm looking at this thing, if someone were just throw it in front of me and say, how do you do this? I would assume you'd try u sub first. But I would end up letting u equal like the entire denominator, and my du would be like 4x cubed plus some other stuff. And then I'd say, wait a minute, 4x cubed is not, it's going to knock out the top, but there's going to be extra stuff left over, and that's no good. So I can't just straight up use u sub on this. If I were going to say, well, maybe it's one of those arc trig patterns that I've heard so much about, I'd say, well, it's got to be arctangent, because arc sine and arc secant both have square roots in the bottom, and this clearly does not. So I'd say that's probably going to be an arctan pattern. But arctangent is just constant squared plus variable squared in the bottom, and there's 3 terms here. Now that's not to say I can't take these 3 terms and write them as just a single quantity squared. Like heck, if this were, you remember completing the square back in your Algebra 2 and pre-calc days? You take half of the middle term and square that. So like half of 4 is 2, 2 squared would be 4. Like I could write this as the square root of the first term minus the square root of the second term and square it. But this almost matches what I'm given in the problem, but it's 4 off, right? Like there's a plus 4 here, and this is a plus 8. But what I could do is I could call this x to the 4th minus 4x squared plus 4. And I could just go ahead and add that 4 on myself, right? This is now the same as the original denominator. This much would give you x to the 4th minus 4x squared plus 4. And by tacking on that plus 4, you're now corresponding perfectly with the original denominator. So let's think of the integral this way. Let's call it 6x over, I'm going to put the 4 first to match the pattern, and then the x squared minus 2 quantity squared second. And do I match this pattern? Let's see. Here, this is my a squared, which means a is 2. This is my u squared, and the thing that's being squared here is actually x squared minus 2. And now that I've defined what u is, I can define what du is. That's going to be 2x dx, which comes super duper close to knocking out the rest of the integral. I would just need to stick a 3 here, and then I can make this times 3 as well. And now my 6x dx will knock out the leftover stuff perfectly. So what this really is now, if I stick a 3 out front and a du at the end, I've accounted for the 6x dx. Well, heck, I could put the du up here for that matter. And this is a squared plus u squared. The a squared is what gives me 4. The u squared is what gives me this quantity squared. And now I can use this arctan pattern. So I've got a 3 that's just there because it's sitting out front. I've got 1 over a, which is 1 over 2, because a is 2. Then I've got arctangent of u over a, which is going to be x squared minus 2 over a is 2, plus my constant of integration. And I guess, before I get too excited here, I'll call it 3/2. So again, this solution was brought to us by the process known as completing the square. It doesn't routinely get tested on the AP test. I mean, it might be a multiple choice question somewhere. It's not worth spending 6 hours of your review time studying for, but it's just a good algebra skill to have at the ready anyway. It's going to get assessed on this homework, so that's another good reason to be familiar with it. All right, so I'm just going to go ahead and admit this. This last one's tricky. If someone were to just slide this in front of me and say, hey, what would you do to solve this? My gut would be to say, well, it's probably a u sub problem. I'm going to let u equal the stuff that's inside the radical there. And then my du is, I'd say, well, that x to the 9th isn't really anywhere in the problem. I'd say that's probably not what I actually wanted to do. So then maybe my next instinct might be to say, can I make it fit one of the arc trig patterns? And looking at the denominator here, there's a radical in the denominator, so I'm probably going to throw arctan out because arctan doesn't have a radical in the denominator. But arcsine does. Arcsine, though, doesn't have anything outside the radical with it. The only thing that matches having a radical in the denominator and like a quantity not in the denominator is an arcsecant pattern. So let's jot down what that is here for reference. There it is. So then I'd go about trying to make this problem fit this pattern. So in order to get u squared as the first term in the radical, I would need to make u equal x to the 5th, because I need x to the 10th ultimately. So x to the 5th squared would give me that x to the 10th. And once you define what u is, you can very quickly define what du is. Then I'd say, well, this second term is supposed to be a squared. In the problem I'm given, it's a 1. So if a squared is 1, that means a would have to be 1. So I've defined u and du, I've defined a. That's everything I need to work with this pattern. So now it's a matter of rewriting the integral in terms of u's and a's instead of x's and dx's. For one thing, I've got this 2 as a constant. That hasn't been addressed anywhere in here. So I'm just going to put the 2 out front because that's a thing you can do with constants. You can just slide them out to the front. Then, to take care of this radical part, at least the denominator, the x to the 10th is u squared, which is exactly what we want it to be, minus the 1 here is a squared, 1 squared. Now I can't just conveniently put a du here. So what I'm going to do, I'm going to go back to what du is. And I'm going to, I need to get rid of this dx in the original denominator. So I'm going to solve this equation, I know in the past we've done stuff where we've gone to the u equation and solved it for x. In this situation, I'm going to go to the du equation and I'm going to solve it for dx. So dx, to get that by itself, would have to be du over 5x to the fourth. So now if I want to replace the dx in the original problem, I can do that with a du over 5x to the fourth. So let's kind of go back and check off what we have accounted for. I have accounted for this, clean this up. I have accounted for this 2 because I put a 2 out front, so that's good. I have accounted for the dx because I put a du over 5x to the fourth in the problem, so the dx is good. And I have accounted for everything inside this radical because I've put square root u squared minus a squared, so that's good. The one thing I have not accounted for is this x sitting out front, and I could, I suppose, just put an x in the problem. I know I'm mixing u's and x's, but there was already x's there, so I don't feel like I'm really introducing an issue that wasn't already there. If I clean up this expression, I now have like 5x to the fourth, or no, 5x to the fifth outside the radical, and then everything in the radical is in terms of like stuff I've defined. And this is only an issue because of that. There's x's and u's and a's, it's a mess. Ultimately, I want to get everything in terms of a. Well, this 5, this is a constant, so that can go out front. So now I got a 2/5 out front. I still have a du in the top. I still have this square root in the bottom. But now I've got this x to the fifth that I haven't accounted for. Gosh darn, if only there were something in terms of u that I could put in to represent x to the fifth. Well, if you go back to your original statement, u equals x to the fifth, this x to the fifth is simply a u. And now we match this pattern perfectly. We just have a 2/5 out front, which is fine. We'll have a 2/5 out front. With that 2/5 out front, the rest of this just follows the arc secant pattern. So we have 1 over a, which for us will be 1 over 1. Then arc secant. U over a is going to be x to the fifth over 1 plus a constant. And to tidy this up a little bit, you simply get 2/5 arc secant x to the fifth. I guess I should put that in absolute values to keep the domain true to numbers that'll work. Was that tricky? Did I take a couple cracks at it? If you go back and watch carefully, you'll see that there was all kinds of erasure marks all over the paper when I started the problem because I deleted my first couple attempts at it. So yes, it's tricky, but that's why we do it. That's why we go through it as an example. Hopefully the homework will seem easy by comparison, and if it doesn't, then let me know and we'll talk about those problems. So good luck to you on the homework and keep in touch with any questions you might have.